In this video lecture, we will talk about the conservation of mechanical energy. When we say that energy is conserved, we mean to say that the total energy of a system remains the same at all times. For example, if a circus acrobat jumped from the top of a very tall human pyramid, the total energy that he has at all points, starting from the top of the pyramid to the bottom where he safely landed, is constant. The catch to this is that although the energy is conserved, it is transformed from one form to another. At the top of the human pyramid, the acrobat only has potential energy. As he falls down, his potential energy decreases since he is approaching the ground, but it is transformed into kinetic energy as he speeds up doing so. On the ground, all potential energy would have been transformed to kinetic energy. Another application of conservation of energy is found on roller coasters. Have you ever wondered how the roller coaster car can roll up the hills and loops of the track even without the assistance of external machines to keep it going? The answer is the conservation of mechanical energy. During the start, the roller coaster is hoisted up to the top of the hill, the highest point of the track. The purpose of this is for the cars to gain potential energy. PE is highest at this point. Once released, the car slides down the winding track at high speed. The potential energy is transformed into kinetic energy. The KE is highest at the bottom of the track. This kinetic energy powers the roller coaster to climb up the next hill, where the kinetic energy then becomes potential energy again. This conversion happens with each hill. No energy is destroyed but is lost to friction between the car and the track, bringing the stop, bringing the ride to a stop eventually. We now then understand the full statement of the conservation of energy, which goes like this. Energy cannot be created or destroyed. It may be transformed from one form into another, but the total amount of energy never changes. In equation form, the conservation of energy looks like this. The sum of the initial kinetic energy and potential energy is equal to the sum of the final kinetic energy and potential energy. Take note that the conservation of energy only applies in cases when no external forces like frictional force is present, as they can decrease the mechanical energy of an object. Remember that frictional force will slow down motion, reducing kinetic energy. Let's take a look at this simulation to understand this better. Notice how the thermal energy increases as the skateboarder is eventually turning into a stop. Transformation of energy makes life on Earth possible. Nuclear fusion in the sun releases solar energy, a fraction of which reaches the Earth. Some of the solar energy is harnessed by the plants through photosynthesis. When plants are consumed by humans, the body breaks down food molecules through metabolism. This releases the stored potential energy in the plants, which allows us to do useful work. We can also consume other animals that feeds on plants or other smaller animals. This is energy transformation in food chain. Some of the plants becomes buried deep into the ground, and after millions of years of compaction, they becomes fossil fuel or crude oil. We then transform this into more refined form such as gasoline. For the longest time, we burn fossil fuels to generate electricity and power our transportation systems. Unfortunately, fossil fuel is a non renewable resource, which means we will soon run out of crude oil to refine and burn. The use of fossil fuel is also responsible for most of the carbon emissions into the atmosphere, which is causing global warming. There are other forms of obtaining energy that causes less environmental consequences, such as harnessing hydroelectric power through dams. The cycle still starts with the sun. The sun evaporates water from the ocean. Later on, rain will return them to the earth, which can be trapped behind a dam. Due to its elevated position, water in the dam has a lot of potential energy, which can be controlled to flow down, push against blades in a turbine that spin to power a generator to produce electricity. As a last note, remember that all systems that transform energy from one form to another have inefficiency. That is to say, it is impossible to attain a 100% conversion. For example, in car engines, not all of stored energy in gasoline is transformed into mechanical energy that allows it to run. Most of the energy is instead transformed into heat energy, which comes out from the system as hot exhaust gases. In food chain, there is inefficiency too. For example, if a rabbit eats a grass and a fox eats the fox does not get 100% of the energy of the grass, as energy is lost further down the line of the food chain. It is then a challenge to inventors to devise ways to harness energy that is more efficient and causes less environmental consequences. After all, our world population is still growing, but our need for usable energy ever increases.